Okay, so let's jump into it. Okay, so today's lecture, we're going to talk about evaluation frameworks. So this is going to be another high-level methodology, but we'll get into those details here. So high-level methodologies like STRIDE are methodologies that are widely applicable. So you can apply them to software, hardware, people, processes, procedures, that type of thing. But at the same time, they're not going to give you a lot of depth. Now with STRIDE, what you're mainly doing is you're looking at one thing. So one piece of software or whatever, and you're doing an analysis of that one thing. An evaluation framework, by contrast, is about comparing more than one thing. So STRIDE, you would evaluate one solution and attack trees, which we'll talk about next class. It's even more specific than STRIDE. You're looking at one property or one attack vector, one goal of the adversary for one solution, but we'll get there next class. So these two are just about a single one. And then with an evaluation framework, you're going to try and compare multiple things to each other. Okay, the idea of the comparison isn't necessarily to pick a winner. So sometimes, you have 5 things that could solve your problem for you, and one is the winner. It's better than the other 4. But usually security doesn't work that way. Usually there's 5 options, and all of them have things that they're good at, and all of them have drawbacks. So an evaluation framework is a way of sort of presenting that information so that you can look through it and first off realize there's no silver bullet, like this is the perfect solution, and then you can start like drilling down and trying to figure out, okay, now I have to prioritize what I actually want and try and do it. And the deliverable is really simple. It's so simple you've already seen what we're going to do in terms of the deliverable itself. The reason that we have a whole lecture on it is that it's harder than it looks. But anyways, it's basically just a graph, okay? So, or a chart. Chart's a better way of putting it. So you're gonna have some rows, and the rows are going to be your solutions that you're comparing. You're going to have some columns, and the columns are going to describe things that you want from the solution, like the security properties you want, but we're going to look beyond security as well. So you've already seen this, like, I don't know, if you're buying a car or, looking at different types of bank accounts or that type of stuff, you've seen these kinds of charts before, particularly the one in the middle where there's like some check marks and there's not check marks and things like that. So that's all the deliverable is. So we're going to make a chart like this that compares a bunch of security solutions, okay? But the art of it is sort of how do we pick the columns that we're using to evaluate it, and then how do we decide whether things get dots or not? It's a neutral presentation of information, meaning you're not trying to sell someone on something. So you're evaluating it usually as a sort of, like, a lot of times people, like a car company might make a chart like this because they want to sell you on their car. And so they're going to have all the dots across the chart and none of the competitors will have them, right? That's not the point of an evaluation framework. The evaluation framework is really about being fair and, trying to try and demonstrate all the different trade-offs that are involved in it. So it's meant to be a neutral evaluation, although some people use this kind of thing to try and promote their own solution. So that's, you'll see that as well. But anyways, for the purposes of this class, we're just trying to do it in a neutral way. And then the other big thing about an evaluation framework is you're trying to look at things that influence security in an indirect way. Okay, so there's more to security than security. So you might have a solution and it might be the best in terms of security, but it might cost $1 million for every user, right? Are people going to use that solution? Maybe not, right? Maybe the cost is prohibitive. So cost isn't a security feature, right? Whether something's expensive or inexpensive, but it sure goes into making the decision about whether you want to use this or not. Okay, and so there's other things like that as well, like usability. Is it easy to use? Are people going to make mistakes? Are people going to hate using it? Deployability, like, do you have to put up a bunch of new servers? Do you have to go around and install software on every user's computer? Do you have to give them a new device to carry around with them? Like, what are the deployability issues? And so these are the kinds of things that even if you have a good security solution that's very strong on security, it might actually, it might prevent people from using it in the long run. Okay. So what you want to do in an evaluation framework is anything that might factor into someone's decision about whether they want to use it or not, you want to take that into account. Okay. The other thing before I go into this, I mentioned it, I think, in the email in just a sentence, but sorry, there'll be a bit of coughing. The assignment 1 will ask you to do an evaluation framework. Okay, so I'll give you a new thing. I've done the same one the last couple years. I may change it or not. I have to talk to the TA and see what he thinks about the assignment. But anyways, you'll actually do this. So anyways, that's just a sort of cue for you to pay attention, extra attention to this. And of course, the video will be here in the slides and all that type of stuff. So you can always come back and look at it. Okay, so the rows are going to be your solutions that you're comparing. And the main thing about the rows is, first off, they should actually be alternatives to each other. Okay, so if I have if in row 1 I have solution X and I have solution Y, it's not the kind of scenario where maybe you do both X and Y. Okay, it's you're either doing X, it gives you one way of doing it, or you're doing Y. Okay, and sometimes you have, like, you might think of software like, I don't know, antivirus software. That's not really like one solution that like bundles so many things together. Like there's a malware, scanner. There's checking out attachments, maybe some IP blocking or whatever. So those are all like kind of individual technologies. And so we'll get to what you do with that in a second. But anyways, you do want to compare things that are truly alternatives. Another kind of thing that you shouldn't do is compare like sort of newer versions to older versions. So like some people would, like an example would be, let's say you're thinking about Wi-Fi security and you're like, okay, I'm going to compare WEP, which is the old Wi-Fi protocol, to WPA 1 to WPA 2, et cetera, et cetera. In this case, WPA 2 is better than WEP. I mean, there wouldn't be a version 2 if it weren't better. Okay, so they're not actually really alternatives. I mean, sorry, they are alternatives, but they're not really. It's not really a decision. I mean, obviously, you're going to choose the best thing. Okay, unless if you have some sort of backwards compatibility issue or something like that. If one thing is strictly better than everything else, then you're going to go for it. Okay, so what we're looking at more are like completely alternative ways of doing the same thing. Apples to apples means that you are comparing the same kind of thing to the same kind of thing. Okay, so I'm trying to think of a good example. So like you wouldn't compare a firewall to a malware, antivirus or something like that, because they're slightly different things. They both have to do with security and keeping your laptop secure, but they don't really ultimately have the same goal. Okay, so you want to try and compare two things. And then the next thing, the next point is that what we do is we try to reduce the things that you want to compare to the idea of it rather than the actual brand of what it is. Okay, so for example, if we're talking about cars, if your car has an electric engine, or if it has a gasoline engine, or it has a hybrid, battery and engine, then those are categorically different. Okay, so that's like a good comparison. Okay, there are alternatives. Well, I mean, a hybrid is technically not an alternative. So if you want to solve the, like, maybe you can do X and Y problem, you can have hybrid and just make it its own row. If it is a valid composition. But anyways, that's good because you're comparing the technologies. Okay, if you're like, oh, a Tesla Model C versus a Toyota Prius, well, one of them has, I don't know, CarPlay and the other one doesn't, and this one, it will show you, if someone's driving in your blind spot with a light and the other one won't, like those kind of things have nothing to do with whether it's electric versus gas. Okay. So it's not, they're just sort of bells and whistles. And Toyota Prius could change tomorrow, right? It could come out with new things, or the Model C could come out with new things, or the Volkswagen or whatever. Okay. So when you have a brand, the brand will change. I mean, the things will change. Okay. So what you want to do is you want to compare the underlying technology, but you can illustrate it with an example. So you could say electric vehicle, for example, a Tesla Model C, but your comparison isn't about the specifics of that brand. It's about the underlying technology itself. Okay. And I'll say we're going to do an example in a second. So this will hopefully make more sense shortly. Okay, so those are the rows. Okay, so your rows are actual, things that you want to compare. Then your columns are what are you going to look at? And so what are the evaluation that you're going to come up with? And this is sort of harder than it seems. Like when you look at the chart and it's done, you're like, oh, that's pretty obvious. But coming up with these off the top of your head and coming up with good ones is difficult. And sometimes it takes iteration. So you will try some columns and then you'll evaluate it and you'll see, oh, you know what? These two columns are exactly the same. They're not really measuring different things, or this column's the exact opposite of this other column. And so I just need one column to capture it, or whatever the case may be. Or here's a column and nothing gets a dot on this column because, it's empty. And so, yeah, so you can iterate it. The second thing we do is we try and phrase the columns positively, meaning you should always want, so think of it as I haven't got there, but you're going to put a check mark or a dot in the column. And so you always want the check mark. Okay. And it's just a question. This is an English thing. Okay. So for example, let's say that there's an attack against this class of thing that you have your solutions, and there's a certain attack that works on some of them, and you want to make sure that it doesn't work on the different solutions, or you want to see what the differences are. Okay. So you could phrase your column as vulnerable to, cold boot attack, and then you would put a check mark beside the ones that are vulnerable to it. Okay. What I'm saying is flip it around, because what you want is it for to not be vulnerable. Okay. So instead of calling your column in English vulnerable to attack, you say it's not vulnerable to attack, or it's resilient to a cold boot attack. Okay. Now the check mark is something you want. Okay. And the reason you do this is that when you look at a chart at a glance, then you don't have to read the columns to see, okay, is this a check mark that I want or a check mark that I don't want? Right. You can just look at it at a glance. And if you see a row that has a lot of dots, that means it's good. Right. And if it doesn't have a lot of dots, it means it's bad. Okay. Whereas if you're kind of mixing the columns and some of them are good dots and some of them are bad dots, then at a glance, it's really hard to see like what's good and what's bad. You sort of have to go through it dot by dot. Okay. So it's a readability thing. It makes the chart easier to read. Okay. And then inside the cells themselves, you can do anything you want. So you can do numbers, you can use words. There's a lot of different things, but a really simple deliverable is that it's just simply like it has the property or it doesn't. Okay. So you use a full dot if it has it. You use no dot if it does not have it. And then depending on the property, you might decide, hey, there is a kind of halfway here. So I kind of want a half dot. It sort of half has it. And so half dots are not strictly necessary. So you can use them or not use them. The best thing is to try not to use them. So try and do either a dot or not. But then if you really feel like, oh, there is a kind of halfway point, then you can introduce the half dot. Okay. And then in your write-up, so you'll have the chart. At the end of the day, you're going to have this chart. That's fine. And then like for things like assignments and things like that, you're going to have a write-up. And in your write-up, you need to say what the dot means. Like fully satisfies or does not satisfy is just generic. But like for this, like vulnerable to cold boot attack, you have to say, okay, a full dot means like this cold boot attack is impossible. And no dot means it is possible or it's really easy. And a half dot means that, I don't know, like theoretically you could do it, but it would cost you $1 million. So probably people aren't going to do it against like a cell phone they find lying on the street, but they might do it against, some really high target computer or operating system. But the point is that what a full dot meant was specific to that particular column. Okay. So what you'll do is in your write-up is you'll say, okay, here's all the columns I'm using. Here's what a full dot, half dot, no dot means for that column. And you'll go through them one by one. And then you'll also write up why, for your solutions, why did you give it a full dot, half dot, and part dot? And the better job you do defining your columns and what it means to have these dots, then it's a lot easier then it should be obvious. Like if you have a really good column, it should be obvious why the solution gets the dot or it doesn't. Okay. So before we do an example, we're going to center the example around passwords. Okay, so the evaluation framework we're going to do is for passwords and alternatives to passwords. And but before we get there, I just wanted to give a kind of primer on passwords themselves and how they work and that kind of thing. Okay, so with a password, what happens is a user comes to a website and they want to register for the first time. So they send their username and they send their password. And what the server will do is it will record it. So it has a database that contains all the users, and it contains all the passwords. Okay. Then the user comes by later and says, oh, I'm Alice. This is my password. And the server will go in the database and they'll do a comparison between the password that's being supplied and the password that they recorded. And if the passwords match, then it's considered the same user. And if they don't match, then it throws an error message of some sort. And then the user might be able to try again, or they might get locked out. There's different things that you can do in response to that. Okay, so let's think of adversaries. So the first adversary you might have is a shoulder surfer. Okay, so a shoulder surfer would be somebody that's trying to look at your password as you're typing it into your keyboard. Okay, and so this could be like an actual physical person that's like looking over your shoulder. That's the example that's given. It might be instead it might be like surveillance cameras or something like that. It could even be like reflections off of your glasses, and there's surveillance on your glasses, so they can't see your keyboard, but they can see a reflection off your glasses, like that type of thing. So there's all sorts of crazy scenarios that academics have even come up with for like things that you wouldn't expect to be able to see, but you somehow are able to see them. So one example, there's a little movie playing in the bottom left. And so this is Edward Snowden, who was a whistleblower for the NSA, whistleblowing on the NSA. And there's both a Hollywood movie about him and an actual documentary. And so this is sort of cut between them. But I don't know if you caught it. I'm going to play it again one more time. But he's putting his password into his computer. And, you know, this is very high sensitive, you know, life or death kind of scenario. And so he's in a hotel room with some journalists. And so you can see he puts a blanket over his head as he's typing in his password. And, you know, just so that nobody could shoulder surf it, like even hidden cameras or that kind of thing. Okay. So that's a sort of extreme example, maybe something that you or I probably have never done, but he felt it was warranted in that scenario to do. Okay, another thing you can do is you can try and pull the password out through software. And in particular, you're going to do it, I should say it could be hardware too. So it could be software or hardware. And depending where on the stack, we might call it different things. So if it's sitting in the operating system, we might call it malware. If it's sitting at a driver level, we might call it keystroke logging. Another sort of real life example that actually happened here at Concordia is someone was walking around in the library. And if you've been to the library, you know they have these computers that you can just walk up and use. And they noticed that there were these weird dongles you can see in the picture where the keyboard was plugged into a dongle and the dongle was plugged into the computer. And so this was keystroke logger. Sorry. So it basically was trying to it was actually recording every single thing that was being typed on the keyboard as just a stream. So that would include usernames and passwords as people were logging in to the server. It's probably one of the very first things that someone does. So if you look at the timestamps of the log of this logger, you would see that 5 minutes went by, no one touched the computer, and then all of a sudden they typed in what looks like a username, and you could probably see that it's a username because Concordia will have a directory or something like that that's public, and then the thing that follows is probably the password. The thing about this too is that you can the attacker can just put it there, and some of them will will have like a internet connectivity or something like that, and so it will dump it on an online server. Or the other approach is just that the adversary will come by. They'll put it on for a week, and then they'll come by, they'll put it in their pocket and walk out. So anyways, so you could have malware that sits and looks at your password. Then let's assume that your password makes it so it made it successfully from your brain through your fingers into your keyboard. It made it all the way through your computer, and it popped out the other end on a network. Now it's off to the server, and you can see that the way I've depicted it, and this is actually deliberate, is that it's in plain text here. So that your password just sitting here. This is your raw password. But what happens is you don't do any cryptography to the password at this point. What you do is you have a channel. So the channel that you send it over, which is called HTTPS, it's providing you the encryption. Okay, so because you have an encrypted channel to the server, then it's safe to paste your password in raw as plain text. And if there's an adversary that's anywhere along the line, they're not going to be able to pull that password out, probably. Okay, it would take a breach of HTTPS. Now, HTTPS is something we're going to spend like the next 3 lectures on. Okay, so you're going to learn all the ins and outs, and you'll learn about whether or not this is actually sufficient or not. But for today's lecture, we're just going to assume that this is a secure channel. So there's nothing the adversary can do particularly here in order to nab your password. Okay, then the final thing is I mean, there's probably more than this, but this is just a sort of a rough accounting of the different attacks. One final thing they could do is they could dump the database off the server. Okay, so if they breach the server and steal the database, then they get all the usernames and all the passwords, not just for yours, but for every registered user. Okay, and so this is particularly bad. Of all of these attacks, some of them, shoulder surfing affects, it's one attack that you do on one user. And if you want to attack a second user, you have to do the attack again. Malware, maybe you write the malware once and you can get 100 computers infected or something like that. And so you can get a couple passwords for one piece of malware. But the database breach, it's like you get all the users' passwords for everyone. So it's particularly bad. So normally what we want to do is we want to do something to protect passwords. And so the easiest approach is we will use some cryptography. And I know that you haven't necessarily took cryptography yet. Some of you have, or some of you might be taking it this term. But there's this thing called a hash function. And a hash function is just, you can think of it as a one-way function. So you put an input into the hash function, the output comes out, it looks kind of random. It kind of looks like what's depicted on the screen here. And there's no way to go back. So you can't start with here and try and figure out what the input to it was. Okay, so that's what one way means. So it's cryptographically designed so that it's really hard to invert that particular function. Now, it sounds perfect. You're like, okay, that's good. Now the problem solved. But it's not perfect because hash functions are also deterministic. So deterministic means if you hash the same thing twice, you get the same answer. Okay, so deterministic is going to be both a pro and a con for us. Okay, sorry, I just need to flip back. Okay, so Okay, the reason why deterministic, we actually need it. We strictly need a hash function that's deterministic, is because if Alice's password is recorded by the website as a hash, right? And Alice comes along and gives her raw password when she's authenticating a second time. So she comes back and says, hey, I'm Alice. Maybe she is, or maybe she isn't. The server has to compare this password that it's receiving to the one that's stored in the database. So what it will do is it will simply apply the same hash function to the password that it got, and it's either going to come out to be the same or it's going to come out to be different. Okay. And so that relies on it being deterministic. So if every time you hash the same message, you got a different answer, then you could never do that comparison to the database, and the whole scheme wouldn't work. Okay. Now, the problem with it being deterministic is if I have a guess, I think, you're a Drake fan, maybe this is your password. And so then I'll try it, right? I know you like to put number 3s in for the letter E or whatever, maybe I have 100 guesses or something like that. But if I hash all my guesses, then I can also start comparing them to what the hash is that's recorded by you, assuming that I'm able to breach the database. Okay. And if I guess right, then I'll get your password. Okay. So even though a hash function is one way, right, that just means you can't start from the end and go back to the start. But it doesn't mean that you can't break it by doing the opposite, by starting at the start and going through it. So if you put a lot of guesses through it, in the right direction, right, from inputs to outputs, then you can see whether it matches. Okay, so what people will do is for a common hash function, like say SHA-256 that would be used in these password databases, is they'll get a dictionary of like every word that someone might use as a password. They'll take other password breaches that didn't use hash functions and add them to the dictionary. They'll take multiple words and glue them together. They'll look at song lyrics and take little snippets. They'll do simple translations like turn letters into numbers and things like that. So they'll do all of these kinds of things. They'll have a huge list. And then what they'll do is they'll hash them once. Now they have a list of hashes, and someone might, spend a month or 6 months creating this. Like they'll try literally every combination that they can. So it's a huge list, and they'll do it once, and it will take them months and months and months to compute it. But once they compute it, then they can share it with all their friends. And now if you breach a password, what you can do is you can say, hey, does this match anything on the list? And that's a lot easier than hashing guesses yourself. Okay, you can just go directly to the list and look this up. The list will be like reverse sorted by the hash. So you'll just look it up and see, oh yeah, this was one of the guesses that they tried. Okay, so this is called a rainbow table. So rainbow tables are something that are real that you can get, you can go online and get rainbow tables for. And so it's just a bunch of passwords that have been hashed according to a particular hash function. So what that means is we can actually do something a little bit better cryptographically. So there's two things that we can do. We can't really prevent it. I mean, ultimately, if a hash function is deterministic, the person can always guess. We can't stop them from guessing. Okay. So we can really do, there's two things that we can do though, that to make the guessing hard. The first thing we can do is we can throw in a random number called salt. And so when I take your password, so the database should actually update. So now you would have the username, you would have the hash of their password and salt, and then you would have the value of salt that you use. So salt is just a random number that you pick. It's stored in the clear text. So if someone dumps the database, they get the salts for every user. So it's not a secret, it's not a key, it's nothing like that. All it is it's a random number. And what it means is that Alice's salt will be different than David's salt. So if you wanted to do a rainbow table, you would have to do it twice. You'd have to do a rainbow table that's for Alice's salt value, and then you'd have to do another rainbow table that's for David's salt value. And if you have 1 million users, you'd have to do 1 million rainbow tables. Okay. So what it does is it kind of ruins this idea that you can do one rainbow table once and it's going to work for all the users in the database. Now it's like you need a rainbow table for each individual user. And so it reduces to you attacking individual users. Okay. So that's the idea of assault. The second thing is, in order to, whether you're guessing at possible passwords or constructing a rainbow table, you have to compute a lot of hashes. Basically, you generate a guess, you hash it. You generate a guess, you hash it. You generate a guess, you hash it. How many guesses can you try in a second? Well, that depends on how fast you can hash. The hashing will be the rate determining step. And hashing is super fast. You know, you can do it in like a clock cycle. Usually, I think most computers have some sort of hardware support for cryptographic functions, okay? So you can generate lots and lots of guesses. So what we might do instead is we might actually slow down the hash function. So instead of hashing it once, we'll say, actually, what we're going to store here is the password hashed 1,000 times, okay? So now it's going to take you 1,000 times longer to just generate one guess. Okay. Now the trade-off is that when the user comes along and says, this is my password, the server also has to hash this 1,000 times to see if it matches what's stored in the database. Okay. So it's slowing the server down as well. Okay. But the trade-off is that the server is receiving authentication requests at a certain rate. Like if it's a busy server, there's probably a lot of passwords that are coming in. So it's going to be computing a lot of hashes as well. But the attacker's like literally doing it as fast as they can. They're just hashing all day. It's all they're ever doing. Okay. So the server is probably not hashing things as fast as the adversary is trying to hash things. Okay. So that's why it makes sense. It makes sense to slow it down for everyone. Okay. All right. So anyway, that's sort of a backgrounder on passwords. Are there any questions? I'll just pause. You can unmute or ask in chat. Okay. Don't be shy to ask. Okay. So now let's go back to the evaluation framework. Okay, so the evaluation framework is this comparison of things. And so the example I'm going to use are alternative to passwords. Okay, so things that you might see instead of a password. So passwords go back to the, I don't know, probably the 70s or maybe even earlier. They've been around for a long time. And even before the web, so you have passwords just on the computer as opposed to the internet and things like that. And so when passwords were kind of invented, it might be like you own one computer, so you have one password and your password's for your computer and that's it. Then the web came along and now it's like, okay, well, most of the web, you don't need a password, but you might have your email and you might have this and that. So now you have like 3, 4, 5 passwords, you know, for the 5 different, you know, websites that you use that require a password. Okay. And the idea was that you would generate a randomish password. You would memorize it. You would never write it down or put it anywhere. It would be solely in your head, and you wouldn't use the same password across multiple websites. Okay. And so this seemed like okay advice when you might have 5 passwords that you have to remember. But today, could you do that? Obviously not. Okay. So, you know, I was looking through my my password file, like my password manager file, and you know, I have, I don't know, over 1,000 passwords, you know, for all sorts of different websites and things like that. And there's just no way that I couldn't memorize all of those, right? It just doesn't work. Okay. So what people do instead is they reuse the same password, or maybe they use part of the password and maybe the name of the website, or there's different like kind of rules that people have for how to do it. Or they write them down or whatever. But the point is that this whole model of passwords is completely unrealistic and nobody uses it. And it also results in a lot of security vulnerabilities where these password databases, we see them getting dumped all the time. And so there's lots of raw passwords. Like if there's some password that you used 10 years ago on some website, it's probably in a database somewhere. Okay. All right. So passwords kind of don't work that well. That's fine. So my question to you, and just drop things into chat. What are some alternatives to passwords? So aside from passwords themselves, have you ever seen something that's not a password that a website asks you to do in order to access your account? Something that's not as simple as a username password. Okay, so lots of suggestions coming in now. Okay, so I'll go through them. So first one's biometric. So absolutely. So you might have a fingerprint, a face scan. I have an iPhone. The iPhone does like a face scan. Okay. I have a MacBook. The MacBook has a fingerprint reader on it. So biometrics are one. One-time passwords or two-factor authentication. They're kind of similar things. So in this case, in a two-factor, what I do is I put my username and password in, and then I'm going to get a random code in addition to it. Maybe over text message, it might come by email. It might come through an app, like an authenticator app, that kind of thing. And so and then a one-time password is just that, where that's the only thing that you use to log in. So in two-factor, you have both the password and the random number. And in a one-time password, you just have the random number, but they kind of result in the same thing. George, go ahead. You have a question? Okay, we'll wait for him. So single sign-on is another one, so that's good. So single sign-on would be like, I already have a username password for Google. I want to play some game on my phone. Do I really have to create a username password for the game, or can I just use the one that I already have for Google? What else? So multi-factor authentication, yeah, is just two-factor, same idea, just different acronym. Physical keys. So there are some like tokens and things like that that you can do. Certificates are another thing. So like a cryptographic key. So for example, if I log in using SSH into a server, generally I'm not, you can do it actually with username password, but sometimes it's just, there's a file on my computer, it contains a cryptographic key. When I press enter, my computer does this like cryptographic handshake with the server, and that's all there is to it. I don't even know that it's happening. But if I sit down on a new computer and I don't have that file, then I'm not going to be able to log in. Backup key codes and push notification. Yeah, so backup codes go to recovery. So recovering account is another thing too. So we could, in our chart, we're going to limit it just to logging in, but then how you back up and recover and things like that, that's like also big. Okay, and then lots of people said like some variation on those ones. So all right, so that's really good. I think we got most of them. There's a few categories I can think of that we missed, but I have slides for each of them. So we'll just double check. So two-factor authentication, multi-factor authentication, one-time passwords, they're all kind of the same base. So you get a code, might come to you over SMS or something else. Why is it called two-factor? So what does factor mean? Does it just mean that you have two passwords? Well, you know, so a factor is, it's more than just another password. A factor is like kind of how you authenticate. So generally we say that there's three factors. So there's who you are, which would be like a biometric. There's what you know, which is your password. And there's what you have, which would be like, I have my phone on me. Okay. And so two-factor means that you're using two of those three factors. Okay. So if you had a password and a biometric, that would be two-factor, because one's something you know and one's something that you have. So somebody that is not you but knows your password won't be able to authenticate. Similarly here, the two factors are, the idea of it is that the password is something you know, and the SMS message is something you have because you need to have your phone. Okay. So if someone doesn't have physical possession of your phone, but they know your password, but maybe they're somewhere else in the world, they're not going to be able to go into your account without getting that physical possession. Now, the problem with this is that SMS goes to a phone number, and your phone number is assigned to you using something called a SIM card. And the reason, all the messages that go to your phone number get redirected to your physical phone, that's like subject to the phone company. And if you call up the phone company and you say, I want to change, I have a new phone and it has a new SIM number, and I want my old number to go to my new SIM. If you can convince them that you are who you're supposed to be by knowing a lot of stuff, so this would be like proof of like knowing like what based authentication, then you could actually get it changed. So this is called SIM jacking. And it's it's a big security thing now, especially because of SMS codes. And so, it isn't actually strictly something that you have, right? So a phone number is kind of, ultimately it comes down to like some private information that you have between you and your phone company. If someone else knows that and they know your password, then they can get your phone number changed, and then they can take over your what you have factor as well. So then what people do is they switch to like authenticator apps and other things. So there's other solutions in this space. But anyways, that's just an aside. Okay, another one, I don't think anyone mentioned this, is graphical passwords. So it's still a password, same idea. It's something something you memorize, should be unique for every website or device that you have. But instead of it being alphanumeric characters, it's some sort of swipe pattern or something like that. So this is one way of doing it. There's other ones like based on pictures, like I show you a whole bunch of pictures and you pick them, or there were some experiments where there's a really complicated picture and then you would click on certain things in the picture, and then that would kind of be like your password. Generally, the usability was better. So your ability to remember the password was better if it was graphical based, as opposed to being like just text, random text. But they really didn't catch on, with the exception, I guess, of Android. And the reason Android does it, I don't think it doesn't have anything to do with how easy it is to memorize. It has to do with how easy it is to type, right? So instead of typing a password, it's kind of hard. And so a swipe thing is just really fast. Biometrics, we talked about. So it could be fingerprint, iris scan, face scan. Those are, I think, the main three. Cryptographic keys or certificates, that kind of thing. So this is like a file this is a strictly what you have. It's a file that's sitting on your computer. A key is like a password. It's just way longer and more random, and you're never going to memorize it. Or you might be able to memorize one cryptographic key, period. And probably a pretty weak one at that point. But basically these are hard to memorize. We'll just call them unmemorizable. And so it's really based on a file that you have on your computer that's storing this key. Now, it might be wrapped in a password, but anyways. Another thing that no one mentioned, maybe people weren't thinking of it as an alternative, but it is kind of an alternative, is some sort of password manager. So a password manager will store your password for you. It will even generate it for you. It will generate it long and random. So if there's ever a data breach, the chances of a rainbow table hitting that password because it's long and random is slim. So it's probably going to be protected as long as there's hash functions on the database. And it will give you a unique password for every site. So if there's a database breach of one website, let's say that they're not using hash functions on their password database, then your account will be compromised on that one website only. It won't get compromised on all the other websites that you might have shared that password with. Okay. And then they do fancier things too, like Apple's. This is what I use. I love it because it works for me. It doesn't work for everyone, but I have an Apple computer. I have an Apple phone. I have an Apple TV. If I want to log into Netflix on my Apple TV, I just, I'm using the interface and it just prompts my phone. It's like, hey, we see that you have a password stored. Do you want to just use it? And I press one button and I'm logged in. Otherwise, I'd be typing in this like really big, long, random thing because it generated it for me randomly. Okay, so it's this is a solution that I really like, but the problem with it is all my security is now in my Apple password. So I have an iCloud account. It has a password on it. If you're able to break into iCloud, then you have all of my passwords, right? So it's like all my eggs are like kind of in one basket with a password manager. A hardware token. So this is someone mentioned. So this is like, it's like a one-time password that you get over SMS, but instead of it coming to your phone, it's like a device that you carry around. Okay. So there's a number that's sitting on the device and it's updating every 10 seconds, or sometimes you push the button and it updates. There's two different models. And then you type it in to the website. We'll come back to this in a couple lectures, maybe, you know, when we talk about social engineering, actually, I'll actually explain to you the details of how this works and the cryptography that's used and things like that. But for now, it's strictly a something you have kind of factor. Single sign-on, someone mentioned. So this is, you know, you sign in with some other account that you have. It's kind of like it's kind of like if you're using an Apple password manager and it's being synchronized through the cloud, then it's ultimately being protected by your Apple password. And so signing in with Apple is basically the same threat model. Okay. Now, a question you might have is, or here's a good question. Why does Facebook do this? I mean, Facebook, like now they have to run a server that's going to take, like I'm logging into some game, right? So I pick up my phone, I want to play a game, and it's like, do you want to sign in with Facebook? So that's fine. But it's not free for Facebook to do that, because now the game is going to call over to Facebook and say, hey, you know, this guy's claiming to be Jeremy Clark. He says he has a Facebook account. This is his password. Can you check it out for us? Right? And then Facebook has to say yes or no. So they have to put up extra servers, extra infrastructure in order to do it. They're generally doing it for free, right? They're not charging the game. They're not like, okay, we're going to charge you 10 cents every time someone logs in, right? So why is Facebook doing this? Like, it doesn't make any economic sense. So that's not a rhetorical question. Think about it and put your answer in chat. All right, so couple brave people went through and they're saying, yeah, data, advertising, increasing brand visibility. So all of those are correct, but the main answer is actually more on the data side. So every single time you pick up your phone and play that game, Facebook now knows it. Okay, so they know, oh, it's 2 a.m. and you're playing this game, right? Because you have to do this sign in loop. Right. And so, and they're like, oh, he's on that website again, or he's on this website again. Right. And so it's a lot of data for Facebook, and then they can turn around and use it for advertising and things like that. And then it also, like other people are saying, it kind of locks you into Facebook, because it's like, say I deleted Facebook a while ago. And so I had to stop and think, well, it's fine. I'm deleting Facebook. I don't use Facebook anymore. But you know, is there a whole bunch of other accounts that I only have Facebook logins with that are also going to get deleted when I delete Facebook, right? And so it locked me into keeping my Facebook account, or it could have done that if I had used it a lot. Okay, so these are all reasons why these big companies will try and get you to use single sign-on, even though it costs them money. Okay, then there's some password adjacent subjects that we'll sort of set up aside. So one of them is resetting passwords. So someone in chat also mentioned the idea of asking security questions. So that's the same idea. You know, if I ask you, you know, your mother's maiden name, or like those kinds of like recovery questions and things like that, that's sort of in the resetting phase. And resetting is important because at the end of the day, the adversary just wants access to your account. So if it's easier to reset your password than it is to just log in, right, then they're going to reset your password instead. Okay. So later, actually, when we talk about social engineering, I'll tell you some stories about like more on the resetting side. But for now, we're just going to limit ourselves. We can only do so much. So we'll limit ourselves to just normal logins and pretend that nobody has ever lost a password or have their password stolen ever. And then there's some other things too that kind of go with passwords that aren't exactly passwords, like CAPTCHAs, which is just sort of rate limiting and trying to prevent bots from trying to log in too many times, generating fake accounts and being able to use the fake accounts once they've generated them and things like that. accounts might get locked out. So if you try the wrong password too many times, it might throw a lock on the username that you're trying to log into. It might put a lock on your IP address. It might look at your location and say, hey, this person just logged in an hour ago in Montreal, and now we're getting a login request from somewhere else in the world. And there's no way that they physically could get to that location in less than an hour. And so this is definitely looks like two different people in two different locations using it. We're not going to deny it, but what we're going to do is we're just going to, maybe you're already logged in and you have a cookie, and so instead of just accepting the cookie, now we're going to require the actual password or something like that. So there might be some extra security that gets put on, or an alert or an email like, hey, there was a suspicious login to your account, check it out, kind of thing. So anyways, these all go along with it. Cookies are another password adjacent subject. We'll talk about cookies at the very end of the lecture, at the end of the course, rather, when we talk about policies and procedures. Cookie policies is one of the things that we'll look at. Okay. Okay, so now what we're ready to do is we have our alternatives. And there's more to this than this, or there's more alternatives than this list, but this is a good enough start just to give an example in class. And I'll say that the example we do right now in the lecture, in your assignment, you should probably do it in a bit more detail. It's a little less detail. But then if you want to pick up an academic paper, then you're going to see even more detail. So like the least amount of detail will be this lecture. Your assignment or a project that if you use this kind of thing in a project, that would be like a higher level of detail. And then like an academic paper, like the one that's on the screen right now, would be the highest level of detail. So this paper is, we're actually kind of replicating this paper in a scaled down way. They came up with sort of the theory of doing comparative evaluations. We'll see their chart on passwords in a second. But for now, I want to start talking about the columns. Okay, so what are the concerns that you might have, or like, is two-factor authentication better than normal passwords? And so you might say, yes, it's more secure. And then I would say, well, what does that mean? What does it mean to be more secure, right? Like, give me a specific column name, and then I can put a dot there, that captures that idea that it's more secure. Okay, so that's what these columns are about. They're about coming up with these criteria. And as I mentioned, there's more to security than security. So you might look at cost, for example. So costs, so all of those kinds of things we put under deployability. So deployability is the infrastructure and things like that needed to deploy. How easy is it to make the system work? And then usability is from the human perspective, right? So for example, is a biometric easier to use than a password? Yeah, of course, right? A biometric is very quick. It's easy to use. So then you'd say, well, I feel like I need a column to capture that idea, right? So then you'll come up with some column that would fall under usability, okay? So this idea of using usability, deployability, security, you don't have to do. It works well for this. It might not work for everything, but it's a good starting point. If you have nothing else to start with it. We call it UDS, and you can, it at least prompts you to think a bit about things beyond security itself. Okay, so we'll go through them one by one. So the first one's usability. So usability is from the user's perspective. Okay, and it's basically like, how easy is the system to use? Deployability is from the person providing the service, and it can be anyone. So if it's a password alternative, it's the website. But if it's single sign-on, it's both. You can do it from the website's perspective, but then now Facebook, they have to put up extra servers like we talked about. So that would be a deployability perspective from their perspective as well. So the service, there's not necessarily one service provider. It might be, you might have RSA, the company that's creating these tokens, and you have the website like Concordia that's having you logged in, and both of them have to do different things. Okay. How easy is it to set up? Costs, infrastructure, that kind of stuff. And then security is obviously why we're looking at it. So like what's the differences in terms of security for these things? And privacy sometimes split out, but here we'll keep it together with security. And I should note that last class we talked about Stride, And so you can use Stride to come up with your security criteria as well. So you can say, okay, what are the like spoofing preventions that we should have in place? What are the tampering preventions? Is there a denial of service prevention that we should have? And so Stride can help you brainstorm what these columns should look like. Okay, so let's we'll go through the exercise of coming up with a bunch of columns, and we'll come up with more columns than we'll actually use in the example. But okay, so I have this idea that that a biometric, I said a biometric is better than a password for usability. It's more usable. If I just have to put my fingerprint on my computer, I like that better than typing in a password. Okay, so now I have to stop and I have to think, okay, why is it like better is too vague? We need to be very like, what is it specifically that makes a password, or sorry, a fingerprint better than a password? And so I would suggest that there's two things. One of them is it's quicker. Okay, so it's easier to use, faster to use, less physical effort. So then I might play around with that and say, okay, here's a good column. A good column name would be like, under usability would be no physical effort. And so if there's no physical effort required, then you get the full dot. And you know, if you have to type in a password, you don't get the full dot, and maybe there's a half dot somewhere in there. The other thing about a fingerprint is I don't have to memorize anything anymore. So remember, the old model of passwords is that you memorize a unique password. Now I can forget it. I don't have to remember my password. I have my fingerprint. It's coming with me anyways, right? So I don't have that burden. So there's nothing for me to memorize. In the passwords, I had something to memorize. Maybe if I have a password manager or single sign-on, I have to remember one password for the single sign-on, but then I don't have to remember passwords for every site. So that would be like kind of a half dot for nothing to memorize. And then if I have to memorize a unique password for every site, like the original password model, then that would be no dot. That would be the worst criteria. Okay. So nothing to memorize, physically effortless. This is an example of the kind of column that I would put under usability. Okay. So it's a little hard without seeing these examples, but I'm going to give you 2 minutes to think about your own. You can also start thinking about deployability and security, but for now, try and think of a few usability columns, or at least ideas behind a column, or some usability property that we could highlight if we were trying to compare different password alternatives to each other. So just drop those into chat. I'll give you a minute or two to think about it, and then we'll see how you do. And be brave, be wrong, just write something. Okay, I'll start answering them, but keep typing as I do it. Okay, so someone says strength. I think they mean the strength of the password. Absolutely, for security. So when we come to security, that will be one thing. Ease of use is sort of what I was hinting at. So a fingerprint is easier to use. Ease of use is good. So easy to use is good. And then you have to think a bit about, can you break it down further? Like, what is it that makes it easy? So like the fingerprint was easy to use it, but it was also easy because I didn't have to memorize it. So you can break it down into smaller bits. Do you need an external device? So then again, so why is that bad from a usability perspective? Well, I got to carry around this token with me everywhere I go, right? So nothing new to carry would be a nice property that I might want. That's usability. Or it might be like onerous to use, or I have to pull it out, or I have to look at it, or whatever the case may be. Costs we'll put under deployability, but it's right. Uniqueness we'll put under security. So we need, if it's like a biometric or something like that, it's obviously not going to work if different users have the same fingerprint. Nothing to carry, same idea and correct. Things like availability, those will put under deployability, but they're right. Yeah, so this is like servers and, is there denial of service, and do I have to have the server on 24/7 and that type of thing. Effortless, same idea. So it should be physically effortless. Acceptability. So we actually have, I have a column based on the paper. We call it maturity. So it's sort of a similar idea of this has been around, people have used it for 20 years. And so maybe there's something to it. Whereas this is like something that someone came up with, 6 months ago and no one knows whether it works right or not. So I think that's a reasonable metric. And I would consider it more of a deployability, but it's actually hard to kind of categorize in all of them. Okay, so redundancy, unique, available, convenient to use. So yeah, so you guys are on the right track. So I'll show you the list I came up with. So it's nothing to memorize, easy to learn, meaning you can learn how to use it. And then once you've learned how to use it, it's easy to actually use it. Nothing new to carry, which was mentioned. Scales to thousands of passwords, meaning that, yeah, like the amount of effort for the first password is some amount, but then you have 100 passwords or 1,000 passwords. It doesn't require, thousands of times the effort. The amount of errors that you make is important. So sometimes my fingerprint doesn't read, or my Face ID, I'm lying in bed and my face is on my pillow, or not so much anymore, but a long time ago we were walking around with masks everywhere, and so using Face ID was not that great. Then Apple changed it so that it could reduce your security because you're reading less of the face, but then it would work with a mask. But if you get a lot of errors, then people are going to do other things. Recovery from loss. So these are things. Deployability. So costs was mentioned. You can think of it as a per user cost. You can think about, do I have to go around and change how servers work? Do I have to put up new servers and things like that? That's something I don't want. So no new servers would be the good thing. Does everyone have to change their operating system or their browser to use it? Or can they just use it? Can it just be done with HTML5, for example? Or do you need an extension or something like that? If everyone has to install a browser extension to use your crazy authentication scheme, then you can imagine not a lot of people are going to want to use it. Maturity, we talked about. Openness was another thing that was out of the paper. Just the idea that if you can inspect it and look at it, it kind of goes to security. So you might be able to spot a security vulnerability, but it also lets you plug and play with your existing infrastructure. So you can write the glue to make this work with your website without changing it. Whereas if it's some closed proprietary thing, then you might have to change a lot of things in your stack in order to use the authentication that you want. So open protocol, you could actually rephrase as interoperability, or interoperable would be the positive statement of it. Okay, then from security perspective, so people are saying, okay, you need a password strength, so it needs to be strong. It's strong because people are going to try guessing attacks. So they're going to try every password possible, and they shouldn't be able to guess the right one. So we'd say that's resilient to guessing. Impersonation would be like, I know a lot about you. So like, I know your favorite things. And so maybe I could guess your password. But if I know a lot about you, I'm not going to be able to guess your fingerprint. But then if you're using fingerprints, maybe I can lift your fingerprint off a glass, 3D print a rubber finger, right? And now I have your fingerprint, right? And so anyway, these are all impersonation attacks. You can think of this as the spoofing part of Stride. And then these would be like more like information disclosure side. But and then you can think about, am I able to see your password? Am I able to attack you by observing your password or your password alternative? Okay. And so in the previous diagram, I just broke it into two. So there's like everything that happens before the password reaches the software, your operating system, your keyboard. We call that sorry, I flipped the names. There's a typo in the slide. This should say resilient to external observation would be everything outside of your computer. So that would be shoulder surfing. And then internal observation would be everything inside your computer. So like malware, keystroke loggers that are running at the software level, that kind of thing. If I'm able to pull it out of the SSL or that kind of thing. Resilient to phishing. So you go to the wrong website, you think it's the real Google, but it's Google with 3 O's instead of 2 O's. And you put your username and password in, then you're going to get phished. Okay, but some things like, say, a password manager, it would say, hey, I don't have a password saved for this website because it's the wrong website, right? And so that would at least give you a chance to, you wouldn't just automatically dump your password into a phishing website. So a password manager would do something about phishing, whereas if you just memorized your password, it wouldn't. Resilient to theft. So can I steal something? Like if I steal your hardware token or I steal your phone, what am I able to do with it? And then third parties, this is more maybe from a privacy perspective. So like, is Facebook, Apple, Google, getting pinged every single time you log in? Okay, so what I'll do is, so these are a bunch of them. The paper even has more than this, but this was good enough to get started. And in our example, what we'll do is, I won't even use all of them. I'm just going to pull a subset of them. So there's a question about maturity. So maturity here means basically like something that people have used for a while. So maturity just sort of goes to age, but it's not just age. It also should capture the idea that it's kind of like widely used. And the reason it was in the paper is that the paper was an academic paper. Sorry. And so it was reviewing both things that are used in commercial applications. So like Google two-factor authentication and RSA tokens and commercial products. So they have a big table. I'll show you the table at the end, and they have a bunch of commercial projects. But then in addition to the commercial projects, they also have a bunch of academic papers that people wrote. So someone's like, oh, I think, a good alternative to passwords would be to do this. They write a paper about it. They don't write any code. Nobody's ever used it. It's just an idea that's in a paper. And so it hasn't really been tested out in real life. So the idea of adding maturity is sort of specific to the academic setting, but it was a way to kind of give a point to like, okay, these are things that people actually use, as opposed to here's some solutions that are just, someone wrote a paper about it and that's it. Yeah, any other questions? Just shoot them in the chat. Okay, so what I'll do is I'll pick a couple of these, and then the next exercise is to say, what does a full dot, half dot, empty dot mean for each of them? And then we have to actually make the chart. Okay, so those are the two steps that are left. So we have our rows. Just let me recap. Okay, so going back here. So we have our rows, so we're going to have 8 rows. So these are our rows. Then we have our columns, all of these, but I'm not going to, it would be too big of a table. So I'm just going to pick some at random, not quite at random, but I'll pick a couple. And then what we need to do next is we need to say what the dots are. So the first one I will do is easy to use or physically effortless. And so I'm going to call it U1, just meaning usability 1. It's the first usability requirement. And in the final chart, I'll just have the acronyms. So this is just to save space later when we make the table. But anyways, okay. So I'm going to define easy to use, and this is very informal. In your paper, you should be a little bit more formal, or in your assignment rather. But if I never need to type, draw, or copy, meaning like say I have my phone and there's an SMS message and it says 1, 2, 3, 4, 5, and then I have to type 1, 2, 3, 4, 5. That's what I mean by copy, not like Control C, Control V kind of thing, right? So if I never need to type, draw, or copy in order to log in, then you get the dot. It's easy to use. There's no physical effort involved. An example would be a fingerprint, right? I just scan it, done. Okay. If I need to do it once, but once I've done it once, then I can log into like say 100 sites by just doing it once. So single sign-on, a password manager that has a master password for the password manager. So to unlock it, you do it once, but then you're in. Then that would be, I would give that a half dot. And then if I have to like put in my password, whether it's typing, drawing, or that should say copy, sorry. Like two-factor authentication would be example here, where not only am I putting a password in every single website I go to, right? But I also now have to look at a text message, I have to copy it character by character from the text message into the website. And if I log into 100 websites, I have to do that 100 times. Okay, so that's the worst in terms of easy to use. It's the worst, like it's the most physical effort of probably all the schemes that we have. We can think of nothing to memorize. So that's another one. So if there's literally nothing to memorize, we'll give it a full dot. If I have to memorize one password for multiple accounts, like a master password, or say I'm doing single sign-on, so I remember my Google password, but I don't remember all the other passwords, I just use my Google sign-on, then I would get a half dot. And if I have a unique password for every site, then it would get no dot. Nothing to carry. So if I don't have to carry anything around in order to use the authentication scheme, which is most of them, right? Then it's a full dot. If I have to carry something, but it's something that like I'm probably already carrying around. So like a good example would be two-factor authentication. So if I'm already carrying my phone probably. So it's, you know, making me have to use my phone in order to authenticate. It's not strictly nothing to carry, but it's close to it. So that's sort of like a half dot in my mind. And then if I carry something new, like here's a RSA hardware token, it's something that you're only carrying around to log in. It's not something you even owned before, you know, I made you start using this, you know, say Concordia makes you use it to log into Moodle or whatever, then it's something new to carry, then you're not going to get the dot. Okay. Now let me pause because it's coming to me now that I should have said this earlier, but this is kind of an art as much as a science. So if you go away and come up with your own columns, you may come up with different ones. And when you look at a column, like we both decide on nothing to carry, you may define your dot slightly different than I do. Okay. So I don't want to give the suggestion that, you know, a class of 100, you know, tasked with evaluating password alternatives are all going to come up with the exact same criteria. Like this is the answer. This is the only answer. Like there's no other column that you could have come up with, right? Okay. What I would expect is that in a class of 100, you know, 90%, 80% overlap across like kind of the whole class, right? So there'll be lots of columns that everyone comes up with and they roughly define them the same way, okay? But there's going to be small variations between them. Like you might not think of mature as a property. That doesn't mean you did it wrong, right? It just, you know, so the academics were thinking different than you were thinking as a practitioner or something like that, okay? So anyways, I'll just emphasize as we go, there's, you know, it's not that I'm not expecting everyone would come up with the same columns defined the same way, but I would expect that this is a good representation of the kinds of columns that you would come up with and how you would define them. Okay, then we can go to security. So for security, I picked up, first off, the most obvious one is can I guess the password or not? Okay, if I can't guess it, that means it's resilient, so it resists the attack. That's the good thing. Okay, so this, remember, I want getting a dot to be a good thing. Okay, so in this case, getting a dot is good, so that means it is resilient. And if it's vulnerable to a guessing attack, then you don't get the dot. Okay, now I split it between online and offline guessing attacks, and I'm just going to do a quick aside on the differences between them. I'll give you an example, and then we'll go back to the evaluation framework in a second. Okay, so this will be a bit of a bunny trail, but okay, so an online guessing attack is, both of them are guessing attacks. So I'm going to try and break into your account. I don't know what and it's just a basic password. That's the only authentication you have. You don't have two-factor or anything like that. And I'm going to do it by just guessing your password. Okay. So there's two ways of doing it. One is I have to go through the website itself. So I'm trying to guess your Facebook password. So I go to facebook.com, I put your username in, and then I put my first guess in, I press enter. Okay. Now, the problem with this kind of thing is even if I script it to automate it, Facebook is going to be like, this is weird, right? There's someone that's trying 10, 100 passwords on this one account, and they're going to do something about it, right? They might lock me out. They might slow me down. Throttling, it's called. So like, it's like, okay, you have to wait a minute before trying again. And then I guess wrong. And now it's like, you have to wait 2 minutes, you know, that kind of thing. They have to be a little careful because maybe my goal as an adversary isn't to guess your password. Maybe I want to lock you out of your account. Well, then if I know your username, I can just go start guessing random passwords on your account, and maybe it will lock you out of your account as well, right? So the lockout might be based on my IP address, but it wouldn't affect you or things like that, okay? But anyways, the point is that if you have very strict front ends of the system, like a bank ATM only lets you, I think, guess 3 times and then it locks your account, then you don't need like super strong passwords, right? Like most bank digit pins are 4 digits or 6 digits. And if you get locked out after 3 wrong guesses, then you're probably not going to be able to guess my password from my bank, or it would take you a long time in order to do it, because every time it would get locked, you'd have to wait a couple of days for it to unlock and et cetera, et cetera. Okay. So in order to resist an online guessing attack, you don't need as much strength. Okay. Now I'm going to argue in a second that a 4-digit bank code, even if I only have 3 guesses, I can actually probably do a pretty good job. And the reason is because a human is choosing it, and because a human chooses it, they're not actually choosing it randomly. It's not a random 4 digits. It's more like 4 digits that match some number, like 1, 2, 3, 4, or something like that. That might be the first thing I guess. There's some pattern to the number that they're picking. Okay. So roughly we say that if it resists online guessing, the number of combinations that people are likely to choose randomly from would be about, I just kind of made this number up, but it's roughly correct, would be like something like 2 to the 64. So this is an enormous number, but it's not so enormous that a computer that was, trying all combinations as fast as it couldn't, crack in a week, month, year kind of thing. Okay. And because we don't know, this is called entropy. We don't have to go into what entropy means, but because we don't know the entropy of everything, like I don't know what the entropy of an iris is or a fingerprint or 2-factor, it depends on how many digits they use and things like that. I'm just for the purposes of this class, I'll just say that if the scheme requires the human to choose it, then we're going to say it does not resist online guessing. If instead it's chosen either because it's some random factor of their body, like their fingerprint or their iris, we're going to say it has at least this many combinations. And if it's a machine chosen random number, like that 2-factor authentication code, like the thing you would see on an RSA token, like a cryptographic key that you would have in a file, then it's going to resist online guessing. Okay. Then the higher bar is, would it resist even offline guessing? So offline guessing is like, I have the hash of your password sitting on my computer, and I can, I have a supercomputer. I'm going to try guesses as fast as I can until until my hash comes out to match your hash, and then I'll know what your password is. And maybe I'll run a botnet and I'll get 10,000 computers around the world to also guess at the same time. Okay. So here I get locked out after a couple of wrong guesses. Here, I never get locked out. Here, on an online guessing, I have to like send a packet to Facebook and then wait for the packet to come back. So that also slows me down. Whereas here, it's just like I ask the computer, the hardware gives me the answer and then I check. Okay, so I'm only limited by the electronics of my setup. That's the only limitation. So I can do as fast as my clock cycles allow, and as fast as my memory and RAM and things like that allow. So in this case, you can guess really, really fast. You can do a lot, and so you need a lot more combinations. So an offline computer can blow through 2 to the 64 combinations. That's not impossible at all for a computer to do. And so you would need at least 2 to the 112. Now, 112 doesn't seem like that much bigger than a number than 64, but this is exponential growth. So going from 2 to the 64 to 2 to the 65, it's actually twice as hard. And if you go from 2 to the 65 to 2 to the 66, it's now 4 times as hard, right? So you're doubling, just by making this number 1 bigger, you're doubling how long it takes, okay? So 2 to the 112 is thought to be impossible. Like even if you had all the computers on Earth, you were running them for the lifetime of the universe, you wouldn't be able to check this number of combinations, okay? It's just it's high. It's cryptographically high. This is like what we would do if we're choosing a cryptographic key. We would do something like this. Okay. Yeah. So basically, well, you'll see it in a second. How we award the dots, but okay. The other thing I want to do is I want to just take another aside to the aside, and I want to talk about why human chosen secrets are bad generally. Even like something like a 4-digit PIN. If I have 10 guesses, I actually have a pretty good chance probably of guessing what your PIN might be, because I'm not going to try 00000 00001 0002. What I'm going to do is I'm going to try and guess like patterns that are more or less likely to be possible. So 4-digit PINs are interesting because you can actually get every 4-digit PIN that you could possibly pick, and you can put it on a slide. So everyone's looking at a slide right now, and in the background there's this graphic, and I'm going to explain it. It looks really complicated, but it's simpler than it looks. And then once you get it, it's actually a really, really cool diagram. Okay. But I'll just mention first off that this is a diagram that represents actual real life 4-digit PINs that people chose. They chose it for a website. So usually with a website, you don't use a 4-digit PIN, you'd use like a longer password. And this also was a long time ago. So I forget the exact year, but it would be like in 2010, 11, 12, something like that. The website was broken into, so someone dumped the password database. And most websites are like, okay, your password has to have a minimum of 6 characters or 8 characters. And, you have to have 1 capital and 1 number and 1 special character, that kind of stuff. This website had none of that. Okay, so like you could, if you wanted to make your password 0 and press enter, you could make your password 0 and press enter. There was no restriction at all on the passwords. And so as a result, there were lots and lots of people who just used the 4-digit PIN as their password for the website. So what the authors did is they got a copy of the breached database, and then they went through and they just pulled out all the people that used a 4-digit PIN. And then what they wanted to do is they wanted to show how popular different 4-digit PINs are. Okay, so some 4-digit PINs like 1, 2, 3, 4 might be way more popular than some other 4-digit PIN that's just randomly selected. Okay, and so what they tried to do is they tried to visualize it. And so this is the visualization. And I have to say that this is probably my favorite picture in all of computer science. Okay, so I hope you like it as much as I like it. Okay, so what we're looking at is you see a bunch of like kind of, well, you see a big bluish thing. It has a kind of weird texture, and there's some weird streaks inside of it. Okay, so let's start with what we're actually looking at. What we're looking at in the big square is we're looking at every possible 4-digit PIN that you could possibly choose. Okay, so every 4-digit PIN is represented in this picture, and it's represented by a little square, a tiny square. And the color of the square is basically a measure of how popular it is. Okay, so if the little square is white, that means almost no one chose it. And if it's dark blue, that means a lot of people chose it, and it's a logarithmic scale. So it means like really a lot of people chose it. Okay, so let's just practice reading this chart. So 1, 2, 3, 4 is probably a popular password, right? So where is 1, 2, 3, 4 on this chart? And how dark is the square? Okay, those are the questions. Okay, so how I read the chart is I take the first 2 digits, 1, 2 of 1, 2, 3, 4, and I'm going to find those along the x-axis. Okay, so the x-axis goes from 0, 0 to 9, 9. And so the first 2 digits are 1, 2. So I'll find 1, 2, and that's going to represent a sort of vertical line or a column in the chart. And then in order to find 3 and 4, what I'm going to do is I'm going to go to the y-axis. And so the second 2 digits will be in the y-axis. So I'll look at 3, 4. Okay. And then where 1, 2, and 3, 4 meet is the password 1, 2, 3, 4. Okay. And you can see that it's a pretty dark square. It's maybe one of the darkest squares in the whole picture. And so that means my suspicion is correct. That is a very popular password. Lots of people like to choose it. Okay. Now, here's my question for you. And again, I'll give you a minute to put things into chat about your idea. What are some other 4-digit, like strictly 4 digits? Okay. Think of 4-digit numbers that people might like to choose. You can either give an exact number or you can give the kind of number it is, like what it might represent. So I'm going to give you 30 seconds to put your guesses in, and then we'll go through them. Okay, so lots of activity. Okay, so there's, I guess, 2 things that I see mostly that most people are guessing. The first I would call like some sort of math, like a number like 1, 2, 3, 4 that has some math property. So like 8888 or 1122, like some sort of just sort of like looks nice from a math perspective. Okay, so that absolutely is it. So it has some sort of pattern. The other 4 digits are based on dates and things like that. So year is the most one that people are talking about. Okay, so years are usually 4 digits. I mean, if you go back far enough in time, I guess they could be 3 digits. But recent years like the year 2023 or things like that would be popular as well. And then there's a few other ideas. Okay, so the 2 that you mentioned, I definitely anticipated. Some people are saying phone numbers as well. Phone numbers are actually kind of randomly assigned. So if you use your phone number, we wouldn't see it in this chart. Probably it would probably contribute to. It would actually not be the worst thing to use, other than I might be able to guess it because of who you are. But if I know nothing about you and I don't know your phone number, it's not a bad thing to use because it would be like more or less random. Okay, so in terms of dates, there's 2 things. So people mentioned years. Some people you mentioned a day in a month, or a month in a year, and things like that. Okay, so a month in a day is a good one to start with. So you can think of, for example, my birthday, I'll tell you, is January 20th. So that would be 0120. Okay, so if I want to find that, I would go over here at 01, and then 20 would be like up here, kind of thing. Okay, so this is what I would look for. Now, my question to you is, you can look here, and I hope you can see my mouse. Just if you can confirm you can see my mouse, because if you don't, it makes this whole thing pointless. I guess you can't see it because I'm looking at the YouTube stream and I can't see it. Oh, people are saying yes. Okay, so it's maybe not showing up on YouTube, but it's showing up on Zoom. Okay, so you can see my mouse is tracing. It kind of looks like a castle from the side, how it has like weird things. Okay, and this weird shape it's really weird. So the first shape is like a vertical line that goes up to 31, then it goes to 28, then it goes to 31, then it goes to 30, then it goes to 31, then 30, then 31, 31, right? Why is that? So everyone's guessing the answer. So those are the number of days in a month, right? So January, the first month, has 31 days. The second has 28. And so why is this a shape? Why can I see this shape? Well, it's because lots of people are choosing passwords that are month, date. Okay. And because they're choosing them, it's creating this shape, because the shape is darker, because these numbers are more common to be chosen. So what's crazy is that, let's say you're like, I don't know, one of those aliens that they found in Mexico, and you come to Earth and you don't know anything about human civilization except for the passwords that people choose. You could actually pull out the Georgian calendar, just based on their passwords by looking at a pattern like this. But anyways, okay, so that's why that pattern's there. And then of course down in the US, they tend to do day instead of month instead of month day. And so you see that this exact same pattern appears, but it's just flipped sort of about the XY axis. Not the axis, but the y equals x line. Okay, so dates are popular. The other thing people mentioned are years. Okay, so a year might be something like, I don't know, now we're in the 20s. Okay, and so 20 years that start, like say 2023, let's find it. So 2023 would be, you can't really see it, would be kind of right around where my mouse is here. You do notice there is a dark streak in the 20s, but it ends around somewhere around 2012. Okay, and so these are actually the years. The reason it ends in 2012 is because that's when the database was leaked. Okay, so it was leaked sometimes in the 2000s, and so that's why there's no newer passwords. But you can see that yes, people choose passwords like the year 2000, the year 2005. It gets really dark around 2005, 2006, 2007. Then it starts to fade out. And then if you go before 2000, you would go back to the 1990s or the 1900s. And so the 1990s would be this line starting up here, and then the 80s and 1970, 1960s, and then it starts to fade out around the 1940s, 1930s. Okay, so this is definitely one of the streaks that sort of stand out in this picture is all these years. Okay, so 19 ... would be this line, 20 ... would be this line. Okay, so I call them mathy. So this is the things like, 4444, 7777. Instead of 1234, it's 9876. So that's kind of popular. Instead of 1234, maybe it's just even numbers. So 2468. And so if you go through the picture, there's more than this. Okay, but this diagonal line also stands out probably when you look at the picture. And so this diagonal line is basically like something like 9595, like someone just said in chat. So it's like the same first two digits repeated a second time will create this diagonal line. And then the special cases where there's little dark marks, ones that are extra dark, are ones like 4444, where there's a special pattern too, or 6969, which I don't know why that one's so popular. Okay, then there's also lots of other things. So you can actually spend a long time looking at this graph, and pretty much every little square you can be like 5683. Like that's really dark, but it's kind of weird. I have no idea why that's dark. And then so that was me, and then I Googled it, and it turns out that a long time ago, when we all had cell phones that didn't have keyboards on it, you could still send text messages, but like to send the letter A, you would have to press 1. And to send B, you would press 1 twice. And to send C, you would press 1 3 times. And each digit had like a couple letters associated with it. So if you wanted to send the word love, you would use the number 5, the number 6, the number 8, and the number 3. And so that became like a short form for it. This was also a musical website that the password breach happened on. So there's a bunch of music references. So Usher has an album called 8701. It was kind of popular, and there's another band, Van Halen, that have an album called 5150, and so that was popular and things like that. So anyways, if you are bored sometime, you can pull up this slide and you can look and try and find other patterns that I might miss. I see like there's a streak kind of here, and there's a streak here, which we talked about, and there's a couple other things that I haven't put on the slide, but you can definitely see that there's patterns. Okay. Now, what's the takeaway from all of this? The takeaway from this is, if I want to guess your 4-digit PIN, I'm not going to guess 0000, 0001, 0002. What I'm going to do is I'm going to start with all the dark squares. Okay. And in particular, let's say I get a dump of like 100 users. Then I'll try 1, 2, 3, 4 across all 100 users. And the chances of at least one of them having that password is pretty high based on how dark this square is. Okay, so sometimes I'm not attacking a specific person. I'm just trying to get access to one in any account. I don't care which account. So anyway, so human chosen secrets, not very secure. Even if you try and be clever, there's tools that build dictionary guessing, dictionaries of words to try and guess, and they know all the tricks that you do because they're programmed by humans that know how people set passwords. People look at the password dumps that are in clear text to figure out how people are setting passwords, and then they make sure that the tool covers it and things like that. So like there's one called Johnny the Ripper that is an automated tool for generating like password guesses. Okay, so anyways, all of this was in service of this idea that offline attacks and online attacks, to be secure against both, you need cryptographic generated keys. Biometrics will give you probably security against online, and then anything that's human chosen, you're not going to have security against either of them. Okay, shoulder surfing is another one. So you can think of resilient, meaning it's not vulnerable. We'll give it the dot. Vulnerable, we won't give it the dot. So like, for example, a fingerprint, you can't really shoulder surf, right? But me typing a password in, you could, or me doing the swipe pattern on an Android, you could do. Now, it depends also how specific you want to be about external observation. For example, if I pick up your Android phone, it's completely turned off, but I see a fingerprint smudge in a certain shape, right? That's something that I'm observing externally. And if I follow that swipe pattern of the smudge, it's probably your password because you probably put it in, 30 times since you last cleaned the screen of your phone. And so it leaves that like kind of thing. And you see it in movies too, where like, there's like some digits that are on like a keypad, and like some of them are more worn down than others. And so you can sort of figure out at least what the numbers are in the password, even if you don't know the exact order. And then you can start your guessing attack based on that. Physical theft's another thing we could think about. And then in terms of deployability, costs would be one. So if I have to pay for every user, I have to pay, if I just have to pay once to set the system up, or I don't have to pay at all. Okay, so then what we do is we take this and we put it in the chart. So you can see that I have my 8 rows. So passwords, biometrics, like an RSA style hardware token, a 2-factor authentication, like over SMS, password manager, a cryptographic key file or certificate, single sign-on, and a graphical password. So those are my rows. We have the columns. And what I'm going to do is I'll remind you what the column is for each of them. So in purple, we'll go through the chart one by one because you probably don't remember which was S1 and which was S2. Okay. And then what you'll do is you'll fill in the dots. Okay. So for example, for U1, we said, is it easy to use? And so a full dot would be like you never have to type anything. Okay. So biometric, you never have to type it. So we give it a full dot. Cryptographic key, it's also a file that's sitting on your computer. So you don't have to do anything in order to use it. So these are the two that get the full dot. Okay. A password, you have to type it in, and you have to type it in. If you have 100 passwords for 100 sites, you have to type it in 100 times. Okay. So that's the worst. So we're going to give it no dot. These two are actually even worse than passwords, because not only are you typing in a password every time, but you also have to copy this code that's on a screen from one device into the other device, right? And that's kind of annoying as well. So it's even more effort than passwords. But anyways, we'll also not give it the dot. Password manager will auto fill in your password, but you usually have to unlock it once. So if there's a master password on it, then you type one password in once, but once your master password is in and it's unlocked, then it will automatically fill in the passwords for you. So we give it a half dot. And again, you could disagree. You could say, well, that's so close to a full dot, then I'm going to count it as a full dot. So different people will come up with different scaling, and that's different scales, and that's fine. Keys, we mentioned it's something you don't have to type anything in. It might be a password wrapped key, then you would give it a half dot because it would look like a manager. So you also will make assumptions a bit about how these things work. So like a password manager may or may not have a different password manager. That's actually going to change this, whether it's a half dot or a full dot. So when you do your evaluation framework and you introduce the idea of a manager, or when you're evaluating at the dot, it doesn't matter where you do it, but you have to state what your assumptions are about the thing as well, if it's going to impact the score. Okay. And the point is to be consistent all the way across. So if I'm assuming a master password when I'm trying to decide about this dot, then I have to assume a master password with all the other dots. Okay. And the other thing you could do is you can split it into 2 rows. So you could say password manager with master password, and then you could have another row for password manager without a master password. Okay. Single sign-on, you log into Google, and then once you're logged into Google, then you don't have to log in for each individual site. And then a graphical password is just like a normal password. It's just you're drawing instead of typing. Okay, the next column actually looks exactly the same, which is basically, do you have to memorize something? So full dot if you don't, half dot if you have to memorize one thing, nothing if you don't have to memorize anything. Now, I left this in actually on purpose because this is something you'll see when you do your evaluation frameworks is U1 and U2 result in the exact same thing, okay? So when you're doing the evaluation framework, you should then think and say, is it actually the same property? I mean, is nothing to use, easy to use and nothing to memorize? They sound like different properties, right? But it looks like they're the same. I mean, if you get the dot on one, you get the dot on the other and vice versa, all the way down. Even all the half dots are the same, okay? And so here you need to really scrutinize whether you should just delete this column or you should try and merge them or something like that. And what I would be looking for is, I would ask myself, well, is there such a thing in the world that would give you a dot on one, but not give you a dot on the other, right? So is there something that you do have to type things in, but it's not from memory, it's from something else. So for example, a one-time password, we don't have explicitly here, but a one-time password is nothing to memorize. So it would get the full dot, but you do have to type it in. And you have to type it in at least for once for every login, okay? So a one-time password is actually an example of why these are different columns. So it's just based on the set of rows that we chose, we didn't find an example of one that's separated along U1 and U2, but they do exist, okay? But anyways, if you ever see this where columns are coming out the same, it's sort of a hint to you that you should spend a little time thinking about whether they're the same column or not. The other thing that might happen is sometimes they come out exactly opposite. So if you get a dot on one, you don't get a dot on the other. And so if they're perfectly symmetric like that, that's another thing. Like maybe you're measuring the same thing twice, one in a positive way and one in a negative way. Okay, so nothing to carry. So passwords, biometrics, you're carrying your finger anyways. Password managers, which is a password, it's in your brain. Keys is a file on your computer. Single sign-on is a password, and graphical is also a password. These are all things that are already in your brain or on your body, so they get a full dot. Two-factor, you have to carry your phone, but you're probably carrying it anyway. So we decided that that would be a half dot. And then your RSA token, that little keychain thing that has the number on it, that's something new that you have to carry that you didn't have to carry before. You forget it, you can't log in. It's kind of annoying. So we're punishing it on U3 by not giving it the dot. S1 and S2 were resilient to offline or online guessing. And so basically, if it's machine generated, we'll give it a dot for both. If it's sort of generated by nature, like random, like a fingerprint, we'll give it 1. And if it's a human chosen thing, like those pins in that heat map that we saw, then we're going to say that it's not secure against guessing attacks. So passwords are human chosen, so they're not secure. Biometrics are nature chosen, so they're sort of secure. They have medium levels of entropy. These are all random numbers. So the RSA token and the SMS, you get a random number. That's machine chosen. So we'll say it's secure against guessing. Password manager, your master password, assuming a master password is this, it is a password and it is a human chosen password. And so we'll give it no dot. Now, this you can quibble a bit and say, well, if I only had one password, I would spend a long time. I might even actually generate it randomly and memorize it as opposed to choosing it. So if I only have to do it once for one password, that's easy. If I have to do it for 100 websites or 1,000 websites, that's a different story, right? But anyways, these are the assumptions that you make when you do these evaluation frameworks. Keys are machine chosen. They're long and they're random. They're the most secure against guessing of everything that's on this. And then single sign-on, it's still just one password like your password manager, and graphical are also passwords that you're choosing. You're going to choose a nice pattern that's easy to remember And lots of people will choose similar looking patterns. It won't look random. Shoulder surfing, basically, if you have to type it in and someone can look over your shoulder, then it's not going to get the dot. So a password plus a code that you're either copying off your phone or off a hardware device, and a graphical password as well, which someone can watch you swipe in. These are examples of things that these are examples of things that are not resilient. These are things that are vulnerable to shoulder surfing. Okay, single sign-on, that this has got to be a typo. Sorry, that should also be empty as well, because you're actually, let me think now. We didn't define a half dot. I copied this out of the lecture notes last year, so maybe I'll think about it and come back to it in a sec. But let's do the full dot. So a biometric can't be shoulder surfed specifically. Like it depends. Also, you have to make some assumptions. Like if I have a high res camera, could I take a picture of your fingerprint or something like that? So, it sort of comes down to how you define it. But for a casual, it certainly can't be it couldn't be surfed as casually as you putting a swipe pattern into a phone while I'm watching you do it. A key is the same. It's a file that's on your computer, so there's nothing to observe. You don't actually type anything. It just automatically gets sent across. And then managers and single sign-on, you can think of as sort of in between the two. So this is maybe where the half dot comes in. So once you've put in your master password, then there's no shoulder surfing, because the subsequent authentications just happen automatically. But once you but if I shoulder surf you on putting the master password in, then I could grab it. So I think maybe I didn't do a good job copying the lecture notes over, but you could introduce a half dot for like, there's one password that's vulnerable to this attack, but the rest of them aren't. Physical theft. So biometrics, can I steal your fingerprint? I can, right? Like you might think I cut off your finger and literally steal it. So that's, a sort of gory example, but possible. But even like I can make a replica of it. If I can get your fingerprint, I can 3D print a fingerprint or a rubber finger and put your fingerprint on it, that type of thing. And a key is a file on your computer. So if I can steal your computer, right, or steal the hard drive in your computer, then I have your key and then I can log in. So it's pure physical theft that gets me access. All the rest of them, there's at least a password or something that should be in your brain about something that that would prevent physical theft from being enough in order to steal it. And then deployability, how much does it cost? So for deployability, it was a measure of cost. And so most of these things are free, right? It's just, you have a website, it has a database, a server, all that stuff that you're running that anyways if you have a website, okay? So going from a password to a password manager doesn't change the cost of things. Costs become a factor when, for example, you have to give everyone a token. If you have to give them a token, and you have, like, say Concordia decides we're going to use RSA tokens, right? Concordia has 10,000 people, so they're going to have to go and buy 10,000 tokens and hand them out. Okay, so that's a cost. Biometrics, the fingerprint itself is free, but it's the reader. So we don't all have readers on our phones or on our computers or things like that. So if I want to have a website where people are logging in with their fingerprint, they need to have a fingerprint reader. And so that's where the cost would come in. So it's on the reader side. And then single sign-on, there's additional costs for like Facebook or Apple that we talked about, where they have to put servers up and they have to answer authentication information now for all the websites that use it. They don't care because they're getting data for it. So it's good from their perspective. It's worth the cost, but there is an actual cost there. And so we try and denote it. Okay. So anyway, so this is just an example. It's kind of rough. You might disagree a bit about the dots and things like that, and that's okay. It's not meant to be, like I say, it's not everyone's going to come up with the same chart, same columns, same dots and all that stuff, but it should be generally representative. So most people will come up with something at least pretty similar to this. Now, going back to the purpose of an evaluation framework, let's say Concordia is like, hey, we've been using passwords and we want to switch to something that's more secure, right? Then you could hand them a chart like this, and then they might say, they did actually switch to two-factor authentication, right? And so it might be because they read out this row and said, we like what we see in this row. Okay. Now, if I ask you which one is best, this chart doesn't really answer it, because there's no solution here. First off, there's none that get dots all the way across. Okay. And for every dot that's missing, there's some other solution that has it, but then it has a dot missing somewhere else. Okay. So what it's telling you is that there's trade-offs. There's no perfect solution. There's solutions that get more dots or less dots. But anyways, then your next best thing might be, well, the best one is the one that gets the most dots. So like, for example, when I look at this, I see keys getting almost all dots across. So I might say, well, keys are the best. Okay. But maybe S4 I really care about, like maybe that's like the most important security property for me. Okay. If it's the most important security property, it's way more important than security 1, 2, and 3, then keys isn't going to be the right answer for me. Okay. So different people are going to have different ideas about what's best. If there's a perfect solution, then it's easy. Then everyone can use the perfect solution. If there's no perfect solution, then you have a bunch of trade-offs, and different people are going to choose different trade-offs depending on what their needs are. Okay. And so an evaluation framework is a good way of not telling people what to do. I'm not telling you should use keys or you should use two-factor. I'm just saying, look, here's the pros and cons. Okay. It's a neutral display. You can look at it and you can compare it to everything else. Okay. So that's the job of an evaluation framework. So it will find the basic solution is that there's no perfect solution. That's the basic outcome. And then given there's no perfect solution, it doesn't tell you what to do. It doesn't try to tell you. Okay. It tries to show you all the things that you might consider, and it should make it easier for you to make that decision by looking at it. Okay. The last thing I'll mention is we only did a couple columns and a couple rows. If you want to see a fuller evaluation framework on the same topic, you can look at the paper. The paper is also linked to on Moodle and things like that. And so you can see they also did like full dots, half dots, empty dots. They had a lot of different rows. So they had some stuff like paper-based tokens, like where you have cards and numbers and things like that written down. And there's some things that are based on like doing math in your head. They're called cognitive authentication. And so they had a bunch of categories that we didn't consider. And then they also like split them up. So for example, when they looked at password managers, the big difference between say Firefox and LastPass was one of them used a master password and one of them didn't. So they evaluated both of them twice. Okay. And then for like two-factor authentication, or actually take biometrics. So like fingerprint, iris, voice. So like instead of just doing biometrics as a whole, they try to get down on the differences between them. You can see that they look mostly the same. So in almost all the columns, they look the same. There's a couple in deployability, like the cost is considered, like voice is considered less costly than iris or fingerprint, presumably because lots of devices have microphones already, right? But not a lot of devices have, almost no devices have iris scanners, and some devices have fingerprint readers. They're somewhat common, but not super common, right? So anyway, so you can get into like fine-grained distinctions between them. But anyways, this is what it looks like in an academic setting. If you love this idea of an evaluation framework, you can do it on anything. So in the assignment, you'll do it on something different. I think in the assignment description, when it eventually comes out, I'll have some links to some other papers that do evaluation frameworks. I think on Moodle, there's a couple other papers that are posted that do evaluation frameworks for different kinds of things. If you want to do it for a project, you can, but it should look a little more like, a bit more like this than it does look like this for a project. For your assignment, it can look closer to this than it can look to this. But yeah, so that's sort of the evaluation framework. The main takeaway from their paper is I'll just read a quote from early on in the paper. It says, so this is about passwords specifically. It says, not only does no known scheme come close to providing all desired benefits, so like nothing gets a full dot all the way across. None of them even retain the full set of benefits that legacy passwords already provide. So your first row is like just the normal web passwords that we already have. And you can see all these like kind of red squares. So the red squares are when it does worse than a normal password, and a green square means it's doing better than normal passwords. And so you can see lots of red throughout it. So it means that in order to make some things better, they're making some things worse, essentially. In particular, there is a wide range of schemes offering minor security benefits. So there's a wide range. So some of the schemes offer minor security benefits beyond legacy passwords, and then there's ones that offer significant security benefits, but then they become more costly to deploy or they become more difficult to use, okay? So some things are just like minor tweaks, some of them are major departures, but then the properties really change. And the overall like conclusion of the paper was there is no perfect solution. And that's actually why you might ask yourself, why do we have these 8 different, like, everyone on this call has probably used 6 of these 8. Okay, maybe you've never used keys before, and maybe you've never used an RSA token, but I bet almost everyone on this call has used a biometric at least once. They've had to use 2-factor once. They've at least had their browser ask them to use the manager, whether they chose to use it or not, right? You've probably used single sign-on before. And if you've used Android, anyways, all the Android users have used graphical passwords, okay? So like we literally are living in this scenario where there is clearly no good solution to this problem. And that's why we have 8 different solutions or 6 or 7 solutions, and we've all used different ones, okay? And different websites do it different ways, and there's still no consensus on what should replace passwords, okay? And so probably nothing ever will. There'll never probably be a winner in this scenario, and this evaluation framework tells you why, is because there is no one solution that's actually better than all the other solutions, okay? Every solution that's better in some regards is worse in other regards. And so that leaves it up to the websites to choose kind of which one fits their needs the best. And different people have different needs, they'll make different decisions. Okay, so that's it for today's lecture. So I'll take any questions that you have. So I'll give you a couple minutes to write them in the chat. You can also just unmute yourself and ask them if you want. But okay, so I'm not seeing any come in, but go ahead and keep typing them up to when I end the call. So assignment 2, I'll release next week. So next week in class, I'll talk about what it is. I'll get you to do a bit of Stride. I'll get you to do an evaluation framework. Usually, instead of you picking the evaluation framework, I'll give you something. I'll say, okay, you're going to do an evaluation framework on this, but so I'll give you the rows, and then your job will be to pick the columns and things like that. But the specifics of that, just don't worry too much about it until I give you the assignment. And then we'll talk through exactly what it means. I haven't decided if I'll just use the same assignment as last year, or if I'll try to do a different thing this year or not, and that will kind of influence what it will look like. But there'll be lots of time next class to talk about the assignment specifically. And then if I give it next week, it will be due in 2 weeks. So you'll have 2 weeks to work on it. So we'll have a class in between where you've had a week to think about it, and then you might have new questions or new problems that you want to ask on it as well. Okay, so that will come out next week. And yeah, hopefully next week we'll be back in person at Concordia. And that's it. So I don't see any questions. So I hope everyone has a good day, a good afternoon, and I'll see you all next week.